Hello and welcome back. We are going to be talking about Chapter 7 today. The title of Chapter 7 is Cellular Respiration. Cellular respiration is also known as aerobic respiration. Aerobic meaning in the presence of oxygen, okay? But we're going to be breaking this up into sections just like before. So the first section, we're going to be talking about one of the main strategies that cells use to harvest energy out of the food that organisms take in. Okay, so remember, organisms eat for energy. Well, the energy that is in the food that organisms eat is in the chemical bonds. So there have to be ways that cells can break those chemical bonds and pull the energy out of the food that we eat. Okay, so remember that energy flows through ecosystems. Okay, so ultimately, all of the energy on Earth comes from the sun. And photosynthetic organisms, or autotrophs, have the ability to harvest energy from the sun and use that energy along with CO2 in the environment to make organic molecules. And when we're talking about organic molecules in this case, we're not talking about organic molecules like in organic chemistry necessarily. We're talking about sugars. Okay, we're talking about glucose and fructose and those kinds of things, taking that CO2 and building it into those carbohydrates. That's going to be the subject of chapter 8. Okay, but those organic molecules that photosynthetic organisms create, other organisms eat. Okay, and then when we take in those molecules, our mitochondria are going to take the energy out of the chemical bonds and use that energy to create ATP. ATP powers most of the cellular work, okay? Doesn't do everything, but it does a lot, okay? And then, of course, we've talked about the fact that no energy conversion reaction is 100% efficient, and so some of the energy that was in those organic molecules is then lost as heat. Okay? All right, so the goal of energy harvesting is to create ATP. This is an overview of cellular respiration, and I don't want you to freak out about everything that's on this slide, but cellular respiration is broken into four main steps, okay? Four main processes: glycolysis, pyruvate oxidation, the citric acid cycle, and oxidative phosphorylation. We're going to talk about each one of these steps in its own video, but I'm going to tell you now, you are not going to have to memorize a bunch of pathways. You're not going to have to memorize a bunch of chemical structures. I'm mostly concerned with what are the starting reactants of each process and what are the products of each process, okay? But overall, per glucose molecule, eukaryotic cells are going to make between 30 and 30 ATPs, okay? Well, one of the main ways that cells have for getting energy out of food, out of chemical bonds, is redox reactions, okay? Redox is short for oxidation, reduction, reactions. Oxidation and reduction reactions are moving electrons around. Remember, electrons are what create the covalent bonds that hold molecules together. So if the energy is stored in those bonds, then the energy is with those electrons. So moving electrons around is synonymous with moving energy around. So when you see this abbreviation, this little e with a negative sign, that is referring to electrons, okay? Well, oxidation reduction reactions, we've got to understand the basics about how they work. when I was a freshman in College Chem 1, my chemistry professor gave us this mnemonic device to remember oxidation reduction reactions, and it's the one that I've always used. There's another one out there about Leo the lion goes grr or something, but this is the one I know, okay? Oil rig. Oxidation is loss. Reduction is gain. Well, loss of what? Gain of what? Electrons. Because electrons, in this context, we're going to be using them as synonymously with energy. Okay? So if a molecule loses an electron, that molecule is oxidized. If a molecule gains an electron, that molecule is reduced. Well, if electrons are synonymous with energy, then we can also think about oxidation reduction reactions in terms of our energy progress curves. So if oxidation is loss of electrons and loss of energy, then we're talking about an exergonic reaction. If we're talking about gaining electrons or gaining energy, then we're talking about endergonic reactions. Oops, sorry. So reduction reactions are endergonic. All right. So again, for oxidation, we're talking about loss of electrons, loss of energy. Those reactions are going to have negative delta G's. For reduction, we're talking about gain of electrons and gain of energy. And so those reactions are going to have positive delta G's. Okay? Well, you can't just turn electrons free in a cell. They always have to be attached or part of a chemical bond. Electrons are too small, they're too energetic, they're too powerful, and they would just shred cells. So you can't just have them running amok, okay? They always have to be attached to something. So in cellular respiration, there's a family of molecules that we refer to as electron transport molecules, and their job is to be the electron taxis. Okay, they're going to pick up electrons from one molecule, they're going to take them, and they're going to deliver them to something else. Well, if they're picking up electrons, then there's an oxidation reduction reaction going on there. If they're delivering electrons somewhere else, there's oxidation reduction reactions going on somewhere else. Okay, one of the things I didn't say earlier is that oxidation and reduction reactions always have to be a pair. If something loses electrons through oxidation, something else has to gain them through reduction. Okay, so in cellular respiration, the main electron transport molecule is NADH. Okay, NADH is nicotine amide. Now, you don't have to remember that long name, and you certainly don't have to remember this chemical structure, okay? But the other thing I need you to know is that NADH can cycle between the NAD plus version and the NADH version, okay? In the NAD plus version, NAD plus is an enzyme cofactor. And remember, enzymes catalyze chemical reactions. They lower the energy of activation. Enzymes that require cofactors cannot do their jobs unless those cofactors are present and attached to them. Okay? So NAD plus is required for the reactions that those enzymes catalyze. It is a necessary factor, and NADH in particular comes from the vitamin Niacin. So if you look at your cereal boxes and stuff and all of those fortifications that are added, niacin is going to be one of those vitamins that's added. Okay, so it's critical to the reactions in cellular respiration. So NAD plus can pick up electrons from the chemical bonds in food molecules, be converted into NADH, and then NADH is going to take those electrons somewhere else and give them back. Okay, so we're shuttling electrons around. So if we think about it in this way, NAD plus is going to gain electrons. Okay, well, when it gains electrons, that is a reduction reaction. Okay, so NADH has been reduced because it gained electrons. Well, after NADH takes those electrons to, say, the electron transport chain and gives them back, when the electrons are given back, given away to something else, then NADH is converted back to NAD plus, and it's been oxidized because it lost those electrons. NAD plus can now go and be a cofactor again and pick up more electrons from another chemical reaction. Okay, so when we have oxidation reactions, say from a food molecule that releases energy, releases electrons, NAD plus is going to accept those electrons and be reduced to NADH. Okay, so oxidation of food, reduction of NAD plus. All right, so again, we're having this cycle. Okay, and this is critically important, and we're going to talk about this a lot, all right? But following the NADHs is going to be really important. Trying to understand how energy flows in all of these metabolic processes, you're going to follow the electrons. And one of the best ways to follow the electrons is to pay attention to what happens with NADH. All right, so again, if we look at this, look at all of these places where we're seeing NADH. FADH2 is another electron transport molecule, so it's like kind of like NADH's first cousin, okay? But if we are moving all of these electrons around, there has to be somewhere for them to wind up, ultimately, because we can't just turn them loose. Oxygen in the mitochondria is the final electron acceptor. This is why this whole process is called aerobic respiration, okay, in the presence of oxygen. Remember we talked about electronegativity and how electronegative oxygen is? Well, you can think about oxygen as being this really powerful electron magnet that's hanging out in the mitochondria. And when glucose or other food molecules are being metabolized through glycolysis, the oxidation of pyruvate, the citric acid cycle, and oxidative phosphorylation, oxygen is sitting here in the mitochondria, and it is constantly pulling those electrons toward itself. Okay, it is this really strong electron magnet. Again, because those electrons have to have a final destination. So when they get to the mitochondria and aerobic respiration is done with them, those electrons are going to combine with hydrogen and oxygen to make water. Okay, well, why do we have to go through all of these steps? Why can't we just take glucose, which is C6H12O6, and break it apart into CO2 plus water plus energy? Because if we did this reaction in one step, the amount of energy that would be released would be way too much for the cells to be able to use efficiently. Think about roasting a marshmallow. Marshmallows are pretty much pure sugar. How easy is it to catch those marshmallows on fire? Really easy, okay? Well, cells can't use efficiently that much energy at one time. So much of it would be lost as heat. It would be extremely inefficient. So instead, we've got to pull the energy out in all these little bitty baby step reactions so that the cells can use it efficiently. But again, all of that depends on having oxygen available in the mitochondria. For these four processes, these four separate processes of aerobic respiration, if oxygen is not available in the mitochondria, only glycolysis can happen. Okay, and we're going to talk about that in the final lecture, or the second to last lecture for chapter 7.